that today. Okay, I think we can get started. And if people join us, then great. Let me just do something here. Okay. So, you're probably seeing, you're seeing here on my screen just the overall course folder on my side. And I always just want to show you guys how to get started from that beginning. So I want to invite you to go into your project folder and then launch that rproj icon right there. Okay, so last time we basically stopped, let me take another step back here and mention, if you're not seeing your partial script like this, it will come again on the Files tab, click on that R button, go into your code folder, and then launch the terrain partial exercise. So we stopped pretty much at we made the plots and exported to file that included all the 5 plots together. And I'm going to do here the same trick as I did last time. If you're not seeing your variables in your environment, you can just click on that button. So you can come here on the grid extraction chunk and just click this button here to run all chunks above this chunk, which is going to get us ready to get going here. And while this is running, because it's going to take some time, or just a moment here, but I just want to show you here. I decided to today take 2 step backs, I guess, based on what we did last time. And I want to show you 2 tricks related to our conversation of slope and also flow direction that I think it's going to be pretty useful. So, right now I have everything ready to continue with the exercise today. But again, I want to return to some of the topics that we talked about last time. So I want to invite you to come. So if you're seeing your table of contents here on the side, if you're not seeing, you can just toggle on and off that button right there. And then once you're seeing it, I want to invite you to come to the slope chunk. So that's like the computing secondary variables and then slope chunk right here. So this is, up until here really was the code that we did last time, right? And even if you just rerun it now, it should work just as well. The thing is, these slope values here are in radians, degree radians, right? So they're ranging from like 0.0005 to all the way to 0.07. So this is the range that we're getting in radians. And then one of the questions we had last time is, what if I wanted to express this as percent slope? So that is not something that the terrain function gives us, just like there's no unit percent, so it's something that we actually have to go the extra mile and calculate ourselves. And I just want to show you how to do that. So if you just come at the end here where we have ST as stars, just add a pipe there. We're going to do a mutate. So creating a new column in this object here, I want to call it PCT for percent. And then really what we're doing is taking the tangent of the radian values. So to do that, we use the function tan, open and close parentheses. And if we look here, the result of this slope function where our radian values are, the column is called values, like that. So you can just take the tangent of the values column, which is again the slope in radians, and just multiply that by 100. So this quick trick here is what would transform our slope from radians to percent. And if we just run that and print it, if we come back on this first pane here, now we see that we have two columns that are printed with the summary there. So one is value, so that would be in radians, and the other one is PCT for percent, which is the slope in percent that is for this field is ranging from 0.05% all the way to 7.4%. Okay, so one thing that I want to mention here is, let's say that we really wanted to continue our analysis, meaning like doing everything else that we're doing afterwards with the slope as percent. What I would recommend doing is, because now we have two columns in this data frame, in this stars object data frame, what I would do is basically just select the percent one and leave the values one out, just so it is very clear that there is only one column in this data set, and that's the one that we'll be using afterwards. So if we were to do that, I would just add a pipe, and we're using the select function from the dplyr package. And again, the select function, I always like to explicitly say what package is coming from. So dplyr : select, and we would just say PCT. So this is how we would calculate the slope as percentage, and then only keep that column. So now if we look here, we only have the PCT, we don't have the values anymore there. And with this code, if you go to the next chunk, I don't really want to change anything else here, but because now the slope stars object only has the slope in percentages, if we just run this and print it, even though our label is still saying rad for radians, I mean, that doesn't really matter at this for now, but I just want to show you that the overall look is the same, right? It's just that the values now are ranging from, you know, I mean, we're seeing here the breaks at 2, 4, and 6%. Instead of before it was, you know, lower than that. So this is just how you would calculate slope as a percent in this case. And the reason why I'm not changing like the labels here and everything else is because I want to invite you to come back to this slope chunk and really comment off beginning on that pipe and then the mutate and the dplyr. The reason for that is we're not going to be using slope as a percent moving forward, mostly because the hillshade function requires both the slope and aspect to be in radians. However, I still wanted to show you the code for if you do this for something, you know, on your research or for a project, you do know how to go from radian to percent. So for the sake of our exercise, I want to keep as radian, but I still wanted to show you the code in case in the future you want to have that as percent. So once you comment off starting at that pipe and the three functions below, you can please just go ahead and rerun that slope object and print it just to make sure that we again have the values back. And also, if you did run the plot code here with the previous values in percent, please just run that again so we have the map back to the actual radian values, which I have now here, and you can see is ranging from, like, the breaks at least are 0.02 through 0.06, so we know it's radians. Okay, so any questions related to what we just did? Any comments? All right, I don't hear anything, so I'm going to keep going. Another thing that I wanted to take a step back and just show you guys is something else that is related to flow direction. So flow direction, if you again go back to your table contents and you go on flow direction, I want you to come back to this code here, or actually not this code itself, but it's more on the map. So you can go, so you have the flow direction code right there. You have the flow direction map code. And what I want to do is ask you to come right after the flow dir map chunk and create a chunk yourself. You don't have to say made changes here. That was just for me to remember that I had to come back here, but create a chunk. If so maybe if you have not created a chunk before, you can come to this C+ button right there, And if you click on it, there's going to be a whole bunch of options. You just click on the R option. It should create a chunk for you right there. And it doesn't give the chunk a title. So I just added my title flow dir map 2 because I wanted to show you a new map of flow direction and talk a little bit more about what these values of flow direction really mean. I think we didn't really go into that detail last class, and I really think it's important to make sense of what those values really mean. So assuming you have this chunk here. Oh, and just let me tell, so Victoria, just to tell you, I'm just doing some follow-up on the previous class. So we have not missed anything on today's actual class yet. So you should be good when we get to that point. So if you have this chunk here now, before I show you what I actually want to show you with code, I just want to come to my console and ask for the help of the terrain function. Because when I was reading more on the documentation, I noticed that there's something important I wanted to show you. Oops. Help. Okay. So what flow direction is doing is really interesting. So for each pixel of our map, you can think of a given pixel as being X. And based on the slope and on the aspect, it is really assigning this pixel a value of 1, 2, 4, 8, 16, 32, 64, or 128 to indicate what is the direction that flow is going from this pixel. So let's say if based on slope and aspect, let's say that this pixel is flowing to the northeast, this pixel will have a value of 128. And on the contrary, if it's flowing south, this pixel would have a value of 4. So really, even though here, and this was something that, you know, the unit of flow direction is really not degree. I actually thought it was degree, but then I read more and understood that it's really not degree. It's just showing you the direction of which is going based on this grid right here. So with that, these values here should really, so flow direction is not really a continuous variable as we're showing here. It's more, you know, it's an integer, but that doesn't really mean that 128 is more than 1. It's just really saying what direction based on this grid flow or the direction of the flow is. And I feel like this plot that we made originally, and we're going to keep it like for when we save the plot as we already did, but I feel like the way that it's showing right here is not really useful to understand, right? Because it's treating the scale as continuous, which makes it a little bit more difficult to see really what breaks are related to what color. And also these breaks here are not the breaks that we have in our data set, or that we should have as far as 1, 2, 4, 8, and so on. So I wanted to show you a little bit of a code that will help us to really see what direction water is flowing in this field. And that's what we're going to do in this chunk right here. So let me get my cheat sheet here. Okay, so we're going to start, and what we're going to do here, you're going to see at the end, we're not going to be saving to an object because I really don't intend to keep using this map moving forward. It's just more so we understand what's going on and have a better picture of what this map means. So we're going to start with a ggplot call. So if you come to this chunk here, let's just start with ggplot. And we're going to leave empty at the ggplot level. We add a plus, hit return, and we're going to use a geom stars. And again, we're using geom stars because the flow direction object, which is the flow dir, is a stars object, right? Is a raster type of object. So we're going to say here data equals flow dir. However, right now I'm just going to print flow dir below here so we see it. It is treating the values of that column as numerical, as we already mentioned. And that's really not what I want because they're not continuous numerical, right? They are integers and I want to treat them as such. And in this case, I will transform this values column to categorical to a factor in our language. So I'm going to do that on the fly. So I'm not going to be saving the change to floater itself. It's just going to happen here within GeoMStars, just so we can visualize it. So to do that, I'm just going to hit return here. So this parenthesis is closing that GeoMStars parentheses. I just want to change, and I want to add a pipe and use a mutate. And then we're going to say values, which is the name of the column, equals. To transform something into factor, we can use the function factor, and then we say what column we want to take the values and transform to factors. So we repeat values. So if I just run this piece here, so you can see what's going on, it's basically taking that floater values that originally were seen as numerical and then treating them now as categories. So we can see the categories here and how many observations we have within each one of the categories. So I'm just doing this again on the fly. This is the data that's coming into stars is basically the result of this entire thing. And it's not just floater by itself, but it's treating values as factors as well. Okay, so we can just, this is pretty much what I wanted to have inside GeoMStars. And let's just run that just so we can see what's going on. So now, because it is discrete categorical values, ggplot is selecting a discrete color scale here for us. And it's really, this is what it's showing us. It's kind of difficult to see. And we don't have that map configuration as far as X and Y, because again, GeoMStars doesn't do that for us, but GeoMSF does. So let's just add a plus, hit return, and use a geom_sf to call our boundary. So we do that by data equals boundary_w. We add a comma and we just say fill equals NA. So boundary W was something that we have already imported on a chunk above. That's why we have it available. And if we run it, this is what we see. So now at least we see the shape of the field. Something else I want to do here is, first, I want to add our theme map. So we got a plus. If you recall, we created this object all the way above where it just like adds our theme to it. And here's the thing. So right now we can really see what direction, based on this grid here on the right, on the help of the function, what direction things are going. However, there's lots of colors and they're all kind of bright and still difficult to really see. What I really wanted to do here is to create a plot for each one of these directions, like separate. So we can see only, let's say, if I wanted to see the values 1, I'll have a plot that would only show the pixels that have values equal 1. There are a few different ways of doing this. One of the ways that we could do this is just filtering the data to only contain, let's say, values equal 1 and only do that plot. That is a way that you can do it, but it's probably not the most efficient way of doing this. And I want to show you now a trick in ggplot that is so useful, that is really like, well, let's just go through it and then we'll talk more about how and why it is so useful. So let's say I want to create one plot for each one of these categories. So we're going to be creating 1, 2, 3, 4, 5, 6, 7, 8, 9, including the not a number, which is everything outside of the boundary. So 9 plots we're going to be creating from this. And to do that, we can add a plus here and hit return. ggplot has a column, or sorry, has a function called facet underscore, and there's a few different options. I want to use here facet wrap. And what facet wrap does is you give it a variable in your data set, and it's going to take that variable, look at the value or look at the levels within that variable, and is going to create a plot for each one of the levels, right? So in our case here, the column is called values. So we're basically just going to use that tilde, that's squiggly line, squiggly, I don't know if that's a word, and then just say values. Okay, so if we run this, check out what happened. I'm gonna, just pop out this output so I can see a little bit larger. So it did exactly what we thought it was going to do. It took each one of the levels of the column values, which now is a vector, so it has categories, it's not numerical anymore, and it's just making a map for each one of those levels. And I think this way just makes it a lot much easier to see what direction things are going. So for example, we can see that most of the pixels are going in the one direction, which again by itself, just saying the one direction doesn't make too much sense. But then if we bring in let me do this. If we bring in this matrix here, they're basically going on the east direction, right? So all these pixels are water is flowing east. And then we also see that the other one that has a lot of points is the 128 category. So 128 is going northeast. So all these pixels are going northeast. The water is flowing in a northeast direction. And then, we basically have pixels in every category, but the most dominant ones are 1 and 128. So pretty much water is running from west to east in this field. And I just really wanted to show you this because I think this really helps to understand actually what's going on with this layer. And also this trick of the facet, I think is really, really, really nice. And it has saved me a lot of headache. I just want to tell you a quick story here. On my PhD, I had a study where we had like 30 side years or 30 years of data collected on the same study. And I had all this data for 30 years, right? And I wanted to show a plot for each one of the 30 years. If I didn't know about faster wrap, I would basically do what I was telling you. I would filter data set by each one of the years, make a plot for each one of the years, and in the end, combine all of them. However, I did have a column in my data set that was year, and it had, the description of what year data was coming from. So I could just come here, do faster wrap till the year, and that would immediately create 30 plots for me, one for each year. So this has so much power that is just amazing. And I just really wanted to show you this in this context of understanding full direction. All right.
Dr. Bassos, can I ask a question?
Yes.
Is it possible to not select a particular column since we don't need the NaN?
Yeah, we could filter like different than not a number. We could do that. I just didn't want to spend more time on this, making it pretty, just because we're not really exporting, but we could do that. Yeah.
Okay. All right. Thank you.
Yeah. Any comments? Any more comments or questions? All right. So I guess at this point we're actually going to get started. So these were all the follow-ups I wanted to give you in relation to the previous class. So now I'm just gonna bring my help to the side because we're not going to be using that anymore, not today at least. And I want to invite you to come to the grid extraction part of the code, which is where we would have started fresh today, following up where we stopped last time. Okay, so why are we doing grid extraction? So all the layers that we made up until now in this exercise, so elevation, slope, aspect, full direction, and hue shade are all raster. And I want to bring them all to a vector format, meaning that instead of having raster grid cell, or instead of having raster cells, now we're going to have grid cells where each grid cell is its own polygon. And that's going to help us to bring all these layers together before we do the management zone. So to do that, here, beginning with the elevation one, you can come here and where we have the elevation values is an object called IDW_pred. So you can add a pipe at the end and hit return. Because we're not changing the size of the cell, we're just really saying those cells that were 10 by 10 as raster, I just want to keep them 10 by 10 as vector as well. So we're really just going to transform this stars object that has elevation to a vector object. To do that, we use the function st_s_sf. So this basically transforms something from another type to SF, which is vector. And then it has a couple arguments that I want to change. So the first one is as underscore points, plural, equals false. So instead of giving us points, it keeps the grid and gives us polygons. We can add a comma. And there's another argument called merge equals false, because I want to keep each one of the polygons having their own ID. So that's basically what's happening with the merge equals false. So if we just run this, I just want to run to show you, you don't have to if you don't want to. Now we see that we have a simple feature collection. So simple feature being an SF vector file of type polygon. And then we have now polygons where we have this var1 pred value. And remember the var1 pred name is coming as an output of the IDW function, but this really just is elevation. So we're going to add a pipe at the end, hit tab, and I really just want to extract the var1 pred column. So to do that, we're going to use the select function, but again, we call the package that's coming from. So dplyr colon select, and we could just say, I mean, you can type var1.pred, but I actually want to rename this and give it a more meaningful name as we move on with this later. So I want to call this lf_m equals var1 pred. So the select function allows you to select a column, but also allows you to rename them in the same function. So that's kind of convenient. If we just run this and print the object, we see now that that var1 pred column is called elevation. And even though we didn't select the geometry, it still kept it just because that it does it by default with SF objects. And then lastly, I want to add a pipe here, hit return, and then I want to use the function row names to column, just because I want to have an ID indexing all these 4032 polygons, and I want to call this ID, this column ID. So to do that, there's an argument in row names to column called var, and I just want to say var equals ID like that. So if you run it and print it, you're going to see now that we have this ID column, which basically goes from 1 to 4032. So it has one unique value for each row, and it has the elevation right there as well. So we just did the grid extraction for elevation at this point. We're going to be doing that for each one of the other layers of slope, aspect, flow direction, and heel shade. So if you come back, if you go lower to the next chunk, I already left you the code because we have just built the same thing for elevation. I didn't want to make you, do everything again. The only two differences here is that the incoming data set is different, of course, because the slope object is the one that has the slope values. And then we're changing the values to slope. So if you just run that and print it, we have slope and then the geometries. You can go ahead to the next one and it's the same thing just for aspect. So again, changing the data set coming in, being aspect now, and calling those values as aspect. If you run that, this is what you get. And then we're going to do the same for flow direction. Again, changing the data set coming in and how we're renaming values. And also for heel shade, same thing, same code, just changing the data and how we're renaming the column. Okay, so we basically extracted this for all of our variables for this exercise. And now what we could do is write to file, extract to file. Each one, or not extract, export to file each one of these layers separately. So we would have like a GeoJSON for slope, one for elevation, one for aspect, and so on. But I actually want to combine them in one object, all of these layers, and then export just one object that is going to be related to the terrain variables. And that's what we're going to do next here. So you can just use the tilde, or sorry, not the tilde, the assign symbol there. We're going to start with the elev_v, so the elevation as vector. as polygons that we just built up above. I'm just going to print that so you can see here what it is. And then, and so now this, we're going to use the function left join here that we talked about yesterday. So if we just use a pipe here, we're going to do a left join. So what left join does is it looks at the data set on its left, which in this case is elevation, and it looks at the data set that you give inside left join, which would be like the right data set. So there's a left and a right data set, and they have to have a common column that has to have the same name in both data sets and has to have matching values as well in both data sets. So it's going to basically merge both of these layers using that same column that both data sets have. In this case, that column is ID. So it's going to look at ID 1 in elevation and ID 1 in each one of the other layers that we're going to do next. And it's going to basically bring together those columns, but making sure that they are referring to the same ID, which means they're referring to the same polygon. So we know that a given polygon now is going to have that ID 1, and it's also going to have an elevation column, and also is going to have an aspect and hue shade and so on. That all matches in space because we're using that same ID column from this data set. In what part?
The part that you just did, because I got an error when I did aspect.
So this chunk here,
Yes.
what is it? What error are you
It
getting?
says it's not found.
Is it saying that aspect doesn't exist?
Yes.
Yeah, so what's probably happening there is, yeah, you probably have not created this aspect object. So what we can do, because maybe this is going to happen for the other ones too, if those incoming data frames are not created in your environment, you're going to have that issue for each one of the ones that we're doing below. So what I would recommend is if you come, so are you seeing your table contents? Okay, so if you go on the grid extraction chunk or heading, and what we want to do is basically run all the chunks above it. So we make sure that we create all those objects before we start doing everything else. So you can just come here and hit that run all chunks above on the grid extraction chunk, because then it's going to basically run all of your script up until that point, and we'll create the objects here on the right. So everything then after that point should work. And this, again, using the run all chunks only works if you didn't leave any errors in any of the chunks above, right? If there was an error and you kind of like put aside, the error is going to basically cut the flow and it's not going to make you through that chunk to get to this point. So if you do that, you're probably going to be seeing like there's a progress bar appearing on the bottom that's just going through all the chunks. And I'll just give it a moment for you to catch up. And I know that when we do this run all chunks, I know that it takes just a little extra moment to run the IDW part, just because IDW takes a little bit longer, but it shouldn't take you too long. And then once it goes through and stops showing you the progress bar on the bottom, if you were successful doing that, like you can check your console, because if any errors occurred in your code that stopped the flow of the run all, you will see that error message last on your console, because that'll be the last thing that it happened. If you're not seeing any errors on your console, like on the bottom here on your console, then it means it ran through all right. And then you should be able to just start doing the grid extraction chunks as well. And now, and just a quick reminder, now that you start running the chunks that we're doing today, you don't want to click on the run all chunks above again, right? You just want to run that specific chunk one by one from where we started today.
On the aspect chunk.
Again, okay, let me help you out. So everyone else, hold on for a moment. I'll be right back.
And I got an error when I ran the.
Oh, yeah, so probably was stopping here. Oh, no, but this is. Oh, okay, so here's what's going on. So our code is transforming this into stars, SDS stars, which is what we need. However, you're missing a pipe right there, so it's not connecting with the code below. So now, if we just add the pipe, so now this should be, yeah, so this now is a stars object. And you can kind of see how here as well we've got an error because sped raster doesn't work nicely with the plot, but a stars does. So that's why we want to have stars objects. Yeah, so now I think here. Yeah, so it was just missing that pipe there too. Yeah. All right, is everyone else, I mean, does anyone else have any issues or questions at this point? Okay, I'll take that as a no, and we're gonna keep going here. So we're gonna come back again to this chunk where we're gonna do the left join. And again, the left join is joining two data sets and using a common column between those data sets to do the merge, to make sure that things are aligning properly. So on the left join here, the data set that I wanna bring in is this lope. So the first one at least is lope underscore V. However, if we do this, if you can just run it if you want, we're gonna get an error. Because it is saying that we're basically joining, we're trying to use the left join function to join two spatial data sets. And there is a function especially for joining spatial data sets, which is st join, I think. But when I was using it, it was not really doing what I wanted. It was doing something different. And my workaround, at least for that, is to transform slope into, so right now is slope underscore V is a stars object, right? Oh, sorry, not stars, it's an SF object. It is a vector object. So I want to transform this into a data frame. So to do that, we're gonna do that on the fly as well, right here inside the left join. So we add a pipe there, hit return just to make it easier to see. Then there's a function called as.data.frame that is basically, I'm just gonna run what I highlighted there so you can see what that does. It basically now creates a data frame where we have that ID, have a slope, and have geometry. So the geometry here is really, we really don't need the geometry on the slope data frame because that geometry is already present on the elevation data frame. And because they're being matched by the ID, that geometry on the slope and on the elevation is really the same. So we don't need that geometry on the slope, and I want to remove that. So we're gonna add a pipe here, hit return, and to remove something, we can also use the select function. So again, we're gonna make sure that it comes from the dplyr package, do the select, and when we want to remove instead of keep something, we just do minus and then the name of the column. So minus geometry. I just want to run only this part of the code so we can see what that does. So that basically creates a data frame that has an ID column and a slope column. And now we're going to join this on our 11_v, which is still a vector file or object that has a geometry. So if you run that, it's telling us that it's joining by ID. So it's making the left join based on the ID column. So it kind of automatically noticed that there was one column called ID that had the same column name and also overlapping values between both data sets. And if we just print out terrain V, so terrain V, which is the product of this join here, it is still a SF object of type polygon that has that ID column, has the elevation, but also has that slope column that now came from the slope data set and still kept the geometry because of the elevation V had the geometry there. So basically now we have one object that has one column for elevation, one column for slope. And that's really what I want to have, is one object where each column is going to be a descriptor of the terrain variables. With that, we're basically going to repeat this step here, just changing the incoming data set. So if you want to copy this left join all the way through like that, just copy that, and then come at the end, you can add a pipe, hit return, and paste it. The only difference now is that instead of slope V, we want to bring in the aspect V, right? So that's what we want to do there. So we're still doing the same thing, bringing the aspect as vector, transforming that data frame and removing the geometry and doing a left join of that with everything. So now the left join, and this is something interesting to notice. Now the left join is happening between the aspect and everything that comes before, meaning elevation and slope together. So if we run this, we get two messages saying that is joining by ID because we're doing two joins, the first one and the second one. And then if we print it, now we have a column ID, one column for elevation, one for slope, and now one for aspect as well. And they're all matching with the geometry because of that ID that we're using across. We're going to do this a couple more times. So add a pipe, hit return, paste again, and make sure that it changed the slope V to flow direction, or sorry, flow dir underscore V. We run that. It's making 3 joins, and each one of them is being made using the ID column. If we print it, we have again ID, elevation, slope, aspect, and flow direction in the geometry. So we're just adding those columns to our spatial vector file. And then lastly, we want to add a pipe, hit return, paste again. And the last one we're going to join is the hill shade underscore V. So if we just run that, we have 4 joins. That's why we get 4 messages. And then if we print it, we have also that hill shade column. And then we still kept all of our 4,032 cells of this vector, or not cells, but polygon cells of this vector file. Okay. So I know there's like, this is a little bit more complicated of a code because we're making multiple joins, and each one of them, we're kind of changing the data set that we're joining on the go. We're not saving these changes to anything. I mean, we're changing in the end, we're saving in the end to terrain V, but right here, this is on the go, right? And I know it can be complicated sometimes because we have pipes outside of the left join, we have pipes inside the left join, but hopefully you kind of understood how we built this from the ground up and created the understanding of how it works. I just want to take one moment here to ask anyone has any questions, anyone has any issues with the code. Was everybody able to run it? Okay, awesome. So now that we do have our one object with all the terrain variables, I want to export that. So you can just come here to the next chunk. I think I left you the code there. At least I have on my partial code. I think I did. So we're basically saving this terrain object to our, so we're getting outside of the code folder, inside the data folder, and saving this as terrain underscore v.geojson. So you can just go ahead and run it. I'm going to get an error just because I already have it, but you should not get an error. It should be smooth. So we do want to export this again, because when we start doing the management zones, we'll bring back in all these variables or all these files that we processed. So now we can use them for management zone creation. Okay, so quick summary here of what we've done. So we brought in a CSV point file that had elevation. we interpolated that. The first is the interpolation using IDW of the elevation data, which then basically created to us a digital elevation map. That's what we did. And then we used that DEM to extract secondary variables of slope, aspect, fold direction, and hill shape. And then we combine all these variables into one object and exported this to file. And now we're basically ready with our terrain exercise. And now next thing that we want to do is to bring soil electrical conductivity layer that was collected for this field and also process that. So go through, understand what is soil electrical conductivity, why is that important, bring in that CSV file, process it similarly to what we did here, export it, and that's what we're doing next. And when we get to the end of that soil electrical conductivity exercise, we will be ready to then move into the zone management zone creation, which I think is really the most exciting part of this. But just, also is interesting to note how we had to go a long way before we got to this point, because we have multiple layers we want to bring in to do the clustering of the zones, and we have to process them, right? All these layers, I mean, just think of how much we had to really work with them and make them in the right shape and format before we can actually use them for zone creation. Okay, so this is the end of our terrain exercise. I'm just going to go ahead and close that. If you want, you can just, to make sure that we start with a clean slate on our next exercise, you can just come here on your environment and you see that broom icon right there. If you hit it and say yes, it's basically going to remove all of your objects from your environment. And again, do not fear to do that, because if your objects are in your environment, it means that you created them, which means that you have the code and you have the data to recreate them if you need. So if you just let's say delete your objects here, you're not losing something forever. You have the means to recreate that object in case you need in the future. So don't be afraid of removing objects from your environment right there.